Hi students, in the previous chapters we had learnt about Mendeleev's periodic table and Dobryner's attempts and Newland's laws of octaves. In this chapter we will learn about the modern periodic table developed by Henry Moseley. This periodic table also tells us how the valency of elements varies as the atomic number increases. It even tells us how elements are classified as metals and non-metals in the periodic table. It even talks about how the radius of atoms varies as the atomic number increases. So let's learn in detail about the latest periodic table we have, the modern periodic table. The next attempt at classification, of all the elements was made by Henry Moseley. Henry Moseley prepared a list of the periodic table of elements in 1913. The periodic table prepared by Henry Moseley is called the modern periodic table, and it is the periodic table that we generally use in our daily life even today. Henry Moseley was from the United Kingdom. Here is a photograph of Henry Moseley. So what did Henry Moseley say? Henry Moseley said that the atomic number is a more fundamental property compared to atomic mass. You see, all the attempts to classify elements, before Henry Moseley, classified elements on the basis of atomic mass. Even Mendeleev, in his periodic table, had arranged the elements in order of their atomic mass. He had not arranged them in the order of atomic number. Moseley suggested that elements must be arranged in the order of their atomic number instead of atomic mass. This is Moseley's periodic table. As you can see, all the elements here are arranged in order of their atomic numbers. This is the periodic table that we follow today. Moseley arranged elements from left to right in the order of increasing atomic number, instead of arranging them from left to right in the order of increasing atomic mass. What is atomic number basically? Atomic number, as you already know, is the number of protons in the nucleus of an atom. So this here is the atomic number. In a neutral atom, the number of protons and the number of electrons are the same. So it is also equal to the number of electrons in a neutral atom. It is represented by the symbol Z. So Moseley's periodic table was actually very similar to Mendeleev's periodic table. The only difference was that he arranged elements in the order of atomic number instead of atomic weight. In his periodic table also, the elements which were placed one above the other had similar properties. For example, lithium, sodium, potassium, all of them have similar properties and they are placed one above the other. Similarly, magnesium, beryllium, calcium have similar properties. They form oxides with the same formulae and they form hydrides with the same formulae. So again, they are placed one over the other. So in this case too, the arrangement is almost the same as Mendeleev's arrangement, just that the order of arrangement of elements is in the order of increasing atomic number, not increasing atomic mass. This arrangement in order of increasing atomic number solved many problems. First of all, it solved the problem that Mendeleev's periodic table was creating with respect to cobalt and nickel. Cobalt has a higher atomic weight compared to nickel, but it was placed before nickel by Mendeleev. This could not be explained. Moseley, however, explained this by saying that cobalt has a lesser atomic number than nickel. In reality also, though cobalt's atomic weight is greater than that of nickel, cobalt's atomic number is actually less than that of nickel. So therefore, the arrangement of cobalt before nickel in the periodic table was solved. After all, cobalt has less protons than nickel. Similarly, the issue of isotopes was also resolved by Moseley in his periodic table. You see, when we were studying Mendeleev's periodic table, we said that the same element can have different atomic weights because it can have different isotopes. So chlorine has an isotope which has an atomic weight of 35 and it also has an isotope which has an atomic weight of 37. So how do you represent isotopes in the periodic table? Moseley solved that problem by saying that since we are arranging atoms in terms of atomic number, all the isotopes of the same element will have the same atomic number. So chlorine 35 and chlorine 37 will differ in atomic weights, but they will have the same number of protons, isn't it? Every element can have only one atomic number, though it can have different atomic weights depending on isotopes. So there you go. The problem of isotopes was also resolved, because since we are arranging in order of atomic number, one element will have only one atomic number. So therefore, Moseley's periodic table solved many of the problems which were there in Mendeleev's periodic table. Let's study Moseley's periodic table in a bit more detail. The modern periodic table, as Moseley's periodic table was called, consists of 18 groups or 18 columns. You can see that all these columns here are groups and they are numbered from 1 to 18. Similarly, it consists of 7 periods. All the rows here are called periods. Understood? And you can see that there are a total of 7 periods. All the elements in the same period are arranged in the order of increasing atomic number, and all the elements in the same group have the same chemical properties. Let's look at the electron configuration of elements in the second period. That will help us understand, how the atomic number changes in a period. These are the elements of the second period. The atomic number of lithium is 3, beryllium is 4, boron 5, carbon 6, nitrogen 7, oxygen 8, fluorine 9, and neon 10. Neon is an inert gas. So you can see that the atomic numbers increase towards the right. These are the electron configurations of each of these elements in the same period. You can see that 2, 1 is the electron configuration of lithium. That's why it has 3 electrons. Beryllium has the configuration 2, 2. Boron 2, 3, carbon 2, 4, carbon 2, 4, nitrogen 2, 5, and so on. So basically, as the atomic number increases, the valence electrons keep on increasing. So in the same period, the number of valence electrons keep on increasing by 1 as we move from left to right in a period. Understood? This is what happens. So in a period, as we move from left to right, the number of electrons in the last outer shell keep on increasing as the atomic number keeps on increasing. An interesting fact, however, is that the number of net shells present in the atom is the same. You see, we had learnt earlier that electrons revolve around the nucleus in distinct shells, isn't it? There's the K shell, L shell, M shell, and N shell. In the case of elements in the same period, the number of total shells is the same. Understood? So all the elements in the second period have exactly 2 shells. Understood? So this is an important concept. Though the number of valence electrons keeps on increasing, though the atomic number keeps on increasing, the number of electron shells in the same period is one and the same. The electrons in the last shell keep getting added. They keep on increasing, but the total shells remain the same. Let's look at the electron configuration of elements in the second group. This group consists of beryllium, magnesium, calcium, strontium, barium, and radium. Again, if you observe carefully, these are the atomic numbers of each of these elements. This is the electron configuration of each of these elements. As you can see, the electron configuration of the elements, further down the group is really complicated. Barium has the electron configuration 2, 8, 18, 18, 8, 2, for example. What you can see, however, is that the number of shells keeps increasing by 1 down the group. So all these elements which have similar properties are arranged in a group in such a way that, as you go down by 1 element in the group, the number of shells increases by 1. So you can see beryllium has 2 shells, magnesium has 3 electron shells, calcium has 4, strontium has 5, barium 6, and radium 7. So as you keep on moving down a group, the number of electron shells keeps on increasing. However, the number of valence electrons remains the same. So all of beryllium, magnesium, calcium, strontium, barium, and radium have the same number of valence electrons. Understood? So you can see that all of them have 2 valence electrons. That also tells us why the properties of the elements in a group are similar. After all, elements which have the same number of valence electrons will lose the same number of electrons in a reaction, isn't it? Therefore, the properties of elements which have the same valence electrons are one and the same, and so the properties of elements in one group are very similar. So in a period, all the elements in a group have similar chemical properties. So basically, as we move from left to right, one more electron keeps on getting added, like this. And the number of shells remains the same. As we move downwards, the number of electrons in the valence shell remain the same, but one extra shell keeps getting added. One more and one more, though the number of valence electrons are the same. Understood? So this is the difference between a group and a period. The periods are the horizontal rows. They have elements with increasing atomic number from left to right. Groups are the columns. They have elements with similar properties and elements with the same number of valence electrons. You must remember all this. In fact, there is one other interesting fact. The period number actually represents the number of electron shells in an atom. Understood? So the elements of the first period have one shell, the K shell. The elements in the second period have two shells, K and L. The elements in the third period have K, L and M. The elements in the fourth period have K, L, M and N shells. So basically, as you go down the group, the number of shells keeps on increasing, and the period number tells us the number of shells in an atom. If I ask you what is the number of shells in the sixth period, you can clearly say there are 6 electron shells in the sixth period. That is obvious because as you keep going down the group, the number of shells keeps getting added by 1. So the period number tells us the number of shells. So there you go. That is an interesting concept. Yet another interesting concept you must remember is that the number of elements in a period is the same as the maximum number of electrons possible in a particular shell. You see, as I had said earlier, as you move from left to right in a period, you keep adding more and more electrons to a particular valence shell, isn't it? So the maximum number of electrons in a certain valence shell tells us maximum number of elements that can be present in that period. Take a look at the first period, for example. The first period has just the K shell. The maximum number of possible electrons in the K shell is 2. We had learnt that there can only be 2 electrons in the first shell of an atom. Therefore, there are 2 elements, isn't it? By the 2n square rule, 2 electrons are possible, and so 2 elements are present. In the second period, you can see that the L shell is also present, isn't it? The second period elements have the K shell and the L shell. In the L shell, there can be 2n square electrons by using the 2n square rule, where n is the shell number. Putting n equal to 2 for the second shell, we have 2 into 2 square, that is 8 possible electrons, isn't it? So 8 electrons are possible in the second shell, the L shell. Therefore, there are 8 elements in the second period. 1, 2, 3, 4, 5, 6, 7 and 8. Isn't it? So the number of possible electrons in a valence shell represents the number of elements in the period corresponding to that valence shell. Take a look at the third period here. The third period has the valence shell as the M shell. Isn't it? After all, the number of shells keeps on increasing as you go down the group. So the third period has the M shell as the valence shell. The M shell, according to the 2n square rule, can have 3 square into 2, that is 18 elements. However, we know that the valence shell can have only 8 elements, isn't it? We had learnt earlier that though the maximum possible number of electrons in the M shell is 18, it actually holds only 8 electrons because of the stability of 8 electrons in the valence shell. Therefore, only 8 electrons can be present in the M shell, and so the third period has only 8 elements. So, all this might seem complicated, but it is all very interrelated. Understood? For example, if there can be X number of electrons in a certain valence shell, in that case only X elements can be possible in that period, isn't it? In the third period, for example, sodium has 1 electron in the valence shell, magnesium has 2 electrons in the valence shell, aluminium 3, silicon 4, phosphorus 5, sulfur 6, chlorine 7 and argon 8. And there you go, the period is over. So all these are facts that you have to remember. Initially this might seem complicated because we have talked about so many things all at once. But slowly, if you go over this video again, go back, rewind, Try to understand things again and again. You'll definitely get it. For now, let's move ahead and solve a problem.